Today I would like to present to you an optimum pipeline-based scheduling approach that fully utilizes the parallel computing capability of generally available multi-core systems. First, we observe that the most CNN libraries adopt the system multi-thread scheduling method for parallelization on multi-core systems. However, we observe that the performance gain is not scalable to the number of available cores. Particularly, the multi-thread scheduling performs poorly on heterogeneous multi-core systems. And the main reason is due to the massive data movement overhead. Here, we use a 4-core example to illustrate our findings. We assume C1, C2 are big cores, and C3, C4 are smaller cores. Note that the popular deep learning libraries, such as NCNN Tangent, MNN, ARM-CL, all adopt the multi-thread scheduling function to distribute the computation task in kernel level. For example, for the 4-core system, each layer can be processed in parallel by 4 threads according to the designer's setting. What we notice in practice is that a typical multi-thread scheduler does not consider the data transfer latency between inference layers and between different cores, and may result in unexpectedly poor performance. Since the parallel threads are processing the same data set, for example, core C1 needs to access data processed by core C2 through L2 cache, which is 4 times slower than direct access through the L1 cache. In contrast, C2 and C3 need to access data from each other through the 20 times slower Level 3 main memory, according to the given architecture. Therefore, our experiments show that the multi-thread execution on all 4 cores perform worse than just running on a big core. Therefore, to truly leverage the multi-core computing capability, we need to consider the data locality effect and have a more effective parallel execution algorithm. Here are our actual test results on a heterogeneous platform with 2 big cores and 2 small cores. We test on the CNN models. The results show that the multi-thread execution on all 4 cores is in fact slower than on just 1 big core. Therefore, the key idea of our approach is to minimize data transfer delay by limiting the needs to go through long delay paths, particularly those data transfers through slow main memory. Our approach is to partition the neural net layer into pipeline stages and assign each stage to a group of cores. Each group either contains only 1 core or multi-core, which share an L2 cache. In this way, we avoid inefficient frequent data transfer through slow memory layer. For the example shown here, we have 2 pipeline stages and 2 groups of cores. The first group contains the 2 big cores assigned to process pipeline stage 1, and the other group contains the remaining 2 small cores assigned to process pipeline stages 2. Note that within each group, we still apply multi-thread processing for the best performance. Pipette was the first pipeline-based parallelization approach for CNN inference to improve the performance of heterogeneous multi-core systems. Pipette used an arithmetic operation count-based performance prediction model to estimate the execution time of each convolution layer, and then assign the convolution layers to pipeline stages. The approach did not consider data movement effect, and the scheduling algorithm is relatively complicated. Now we begin to discuss our approach. For a given multi-core architecture, we first identify all possible CPU core grouping configuration. For example, for the demo 2B2S 4-core case, we have the possible configurations of 2 groups and the 4 groups as shown in the slide. Note that in practice, we consider only those groups with all internal cores to share at least the same last stable cache to avoid infeasible data transfer overhead. Therefore, a group cannot contain all 4 cores, as the inter-core communication needs to go through expensive main memory. Then for a given CNN model, we analyze the timing information based on the input data size on each possible group or course. Mainly, we apply the reuse distance method to estimate accurately the data transfer delay. The number of groups determines the number of pipeline stages, and then for each grouping configuration, we find the optimum pipeline partitioning that gives the best pipeline execution time. Finally, the grouping and the corresponding pipeline partition that gives the overall best throughput should be the final best solution. However, the challenge for timing analysis is that the concurrently executing cores generally may suffer performance loss due to the contention effect of the shared caches, as illustrated in the left figure. The figure on the right-hand side shows the result of contention delay overheads for different layers of 3 selected CNN models. Note that the contention delays vary a lot, even for different layers of the same model. Let me briefly summarize what we have discussed so far. Due to the complicated contention effect, traditionally it is impossible to determine the best grouping of cores in advance and to evaluate the workload of each pipeline stage. Therefore, the pipeline configuration optimization can become a labor-intensive trial and error process. Additionally, when the number of cores or the number of layers increase, the complexity increases dramatically. Also, the work needs to be repeated for different hardware platforms or models. Therefore, our most significant contribution is that we apply the reuse distance analysis and achieve very accurate timing estimation for the pipeline optimization. We find that the well-known reuse distance analysis can be effectively applied for our purpose. The reuse distance for a specific data, such as data A in the slides, is the number of different data between the repeated access of data A. Then a reuse distance histogram, which shows the occurrence count of each reuse distance number, can be used for cache miss rate estimation. Without going into detail, we simply state the result. Basically, we may use the cache size to estimate the cache miss rate. As shown in the picture, the red area is the L1 cache miss count, and the green portion is the L2 cache miss count. The good news is that the CNN computation has a regular data access pattern that can be pre-analyzed to generate the reuse distance histogram information. Then once the hardware configuration is given, cache hierarchy and sizes are known, we may easily estimate the delay impact of concurrent executions based on the cache miss counts. Here we show 2 examples to explain how to use the reuse distance for delay analysis. For the first example, that has every core form a separate group. Then C1 and C2 have to share the L2 cache. Therefore, the effectively available L2 cache size becomes half. Consequently, we may use the halved L2 size to estimate the cache miss delay. And the difference to the ideal case of having the whole L2 cache should be the delay overhead of the concurrent execution in this case. For the second case, the multi-thread execution on both C1 and C2 forces them to exchange data on the L2 cache level. Therefore, the original L1 direct access will become L2 accesses, as indicated by the red area. Again, we then use this information to estimate the delay overhead and adjust the timing estimation. With previous information, we can then correct the timing estimation based on the ideal single core case. With the grouping result and the timing estimation, we are ready to perform layer 2 stage allocation. For simplicity, in this paper, we consider only the CNN models with no feedback loops. We then use an acyclic graph to model the given CNN model, with each node representing a CNN layer. As previously discussed, we can annotate the estimated timing information on each node according to the grouping configuration for partitioning optimization. with the given grouping configurations. Essentially, the number of groups determine the number of intended pipeline stages. A general principle of the pipeline optimization is to minimize the workload imbalance or bubbles for the best performance. We hence apply a greedy by partitioning approach to find the optimal result. For each grouping configuration, we assume there are 2 groups only. Otherwise, we simply form 2 virtual groups for our purpose. Then we progress through the CNN graph in the breadth first order and find the partition that leads to the minimum difference of the workload. Note that since the goal is to have all pipeline stages have similar execution times, and each stage is assigned to a group. If any virtual group contains more than one physical group, we shall adjust the partitioning criteria to have the workload ratio between partitions as close as possible to the ratio of the number of physical groups of the 2 target virtual groups. Finally, we may perform recursive partitioning if there are more groups in a virtual group until each partitioning is assigned to only one group. We test our pipeline approach on a ROC 960 board with 3 CNN models, including Mobile FastNet, MobileNet, and SqueezeNet. The ROC platform has 2 big ARM cores and 4 little cores. We feed a continuous stream of 50 images to each CNN model and record the average throughput in terms of the number of images processed per second. We compare our result with multi-thread execution. Note that the 6-core result is very poor due to the data transfer overhead through main memory and hence is not included for comparison. We then tested the proposed pipeline execution. The experimental results showed that the 3 pipeline configurations always perform much better than the multi-thread version. On average, the pipeline performance is 73% better than the best 2 big core multi-thread execution result. We also experimented on the mobile FastNet model using different input data sizes. We found that for cases of smaller input size, the pipeline configuration with 1 core in each group produces the best throughput. The main reason is that the core-specific L1 cache seems to be able to hold data requirement with minimum data miss and transfer, and hence it achieves the best performance. In contrast, for cases of larger input data size, the 2B4S pipeline configuration case gives the best result that minimizes the data transfer impact and produces the best throughput. Now, conclusion. First, we showed that the pipeline scheduling approach for CNN inferencing is on average 73% better than the best multi-thread scheduling result. We also demonstrate that the data contention effect has a significant impact on CNN computing. One of our future work is to extend the pipeline approach to models with feedback loop. Thank you for listening.